7.7 Energy and Equilibrium, the law of the thermodynamics. Okay, so here we already know what's the spontaneous reactions, the reaction that you doesn't need to do any work or put any energy into the system. It's just happening by itself. The spontaneous reaction, the one that given the necessary activation energy, proceed without continuous outside assistant. Okay, so what is the first? There is a 3 law for the thermodynamics. This is the first law. The total amount of energy in the universe is constant. Energy can be neither created or nor destroyed, but it can be transferred from one object to another or transferred from one form into another form. So far, we have seen what is the delta H, that the energy released or absorbed when a reaction happening. So here is enthalpy changes and spontaneity. So what is the bound energy? The bound energy is the minimum energy that you require to break 1 mole of bond between 2 particular atoms, like what? H and H, there is an energy between the bound. If you want to break this bound, the energy will be absorbed, right? They require energy to break a bound. When you want to form a bound, the energy will be released. So these are the energy between the bounds, as you see. So the bigger the energy it is, means it's stronger, it's more stable. So enthalpy and entropy changes. What is that? So enthalpy change, we have seen it before. If the delta H is negative, so it's going to be exothermic reaction. Delta H positive, going to be endothermic. Endothermic, when the energy is going to be on the reactant side. Some of the endothermics are spontaneous. Some of the endothermics could be non-spontaneous. So it really depends. So entropy. The entropy is a measure of the randomness or disorder of the system. When we talk about the delta S positive, means the disorder, it's going toward more disorder. The delta S is negative, is you're going toward less disorder. Okay, what is the disorder? We'll talk about that. You know, when you have a card and you have it in order, but you throw it in the air, it will land on in a random. So it's going from order to the disorder, right? So here is the possible situation. When you have this molecule and the volume is increasing, what's happening, it's going to the higher entropy. Means when you increasing the volume, the entropy or disorder will increase. Also, when you're going from the lower temperature to higher temperature, because the movement of the atoms become faster in a more random way, so the disorder increase from lower to the higher. So increasing temperature will increase your entropy. Also, when it's going from solid to the liquid, the delta S or entropy increase or disorder, it become more disordered because it's more free to move. Also from liquid to the gas, it will be more disordered. Also look at that, when you have a gas, 2 mole gas here, but at the right side, you have a 4 mole gas, 3 and 1 is 4 mole. So it become more disordered. Here, the same thing, 6 plus 1, 6 mole of the gas you have, and here you have 12 mole of the gas. So from 6 mole of the gas, you go to the 12 mole of the gas, so it means entropy increased or disorder, you have more disorder. Same things, from liquid to the gas, you will produce more disorder material. Okay, here's an example. Predict whether the changes in entropy is positive, negative, or following changes predict the spontaneity. Explain your answer. So solid carbon dioxide goes to the gas. Of course, the gas is more disordered. The movement of the gas is much more freely. The atoms in a gas is more freely to move compared to the solid. So the delta is going to be positive. So here is the change will tend to occur spontaneously when the delta S is positive. So the change or this reaction going to be spontaneous. So here is 1 mole of N2O4 going to 2 mole of NO2. So the number of the moles in a gas stage increase. So so it's going toward more randomness. Well, delta S is going to be positive. This reaction will be spontaneous. The synthesis reaction between the oxygen and hydrogen form liquid. So oxygen and hydrogen in the gas state. Go to the liquid, so it's going to be less disorder. The delta S is negative and is non-spontaneous reaction. To practice, you can do question number 1. This is page 498. So we're talking about enthalpy, entropy, and spontaneous changes. We know what is the delta H. We know that the delta S is entropy. Delta H is enthalpy. Now, what is the free energy? Free energy is energy that is available to do useful work. It's kind of an example here. If you have 2 tanks, aquarium 1 and aquarium 2. The temperature in aquarium 2 is much more higher than temperature in aquarium 1. So thermal energy is 70 joule, and here is 100 joules, 30 joule more than that. Also, because of this height here, see, this is not level with this. So this height here, so is the gravitational energy here is 30 joule more than that, which is two of these levels is in the same level. Here is 0. Okay, if you see a fan here, right? Both of that has a fan. If you remove this barrier, what happened? The water come and hit the fan and it's kind of rotate. So kind of the energy here, it turn into the mechanical energy doing some work. But if you move this barrier, nothing will happen to the fan. No work is done, right? So still the energy, as you see, is fixed, but it's turning from one form to another form. It's going to be spontaneous, true? So it's important that we talk about the Gibbs energy. So in general, a change at constant temperature and pressure will occur spontaneously if it is accompanied by a decrease in Gibbs free energy. Changes are spontaneous if the change in Gibbs energy is negative. Okay. So, just a little bit. So here, this energy, some of the energy will go to the thermal energy, will be wasted. See, 70-15 of that going to the thermal energy. Some of that will going to do the work. True. So it's the useful work, and some of that going to the thermal energy, but total energy is constant. So that's why the difference between these two, we have a loss of the energy. So the Gibbs energy here is decreasing. So now second law of thermodynamics is saying all changes in either directly or indirectly increase the entropy of the universe mathematically. So means the universe going through a disorder state. So if we want to predict the spontaneity, we have to look at what happening to the Gibbs energy. Gibbs energy is the delta H enthalpy minus temperature multiplied by delta S entropy. And make sure the unit of all of that should be kilojoule or joule. Here is kilojoule, delta S is kilojoule, and temperature is in Kelvin. If the change in delta Gibbs energy is negative, so it's spontaneous, and if the delta G is positive, it is non-spontaneous. Looking at the Gibbs energy, if the delta H is negative and the delta S is positive, means it's exothermic and is going to more disordered state. then negative and negative, negative plus a negative number will give you the delta G to be negative, true? And we said that if the delta G is negative, that the reaction is spontaneous. So in other words, if your reaction is exothermic and its entropy is increasing or is positive, this reaction is a spontaneous reaction. In this one, if the delta H is positive, it means endothermic, and delta S is negative, is going toward less disordered state. So here is negative and negative positive. Two positive number add together is positive. The delta G will be positive, and it's going to be non-spontaneous reaction, like 3O2 going to 2O2. So the number of is going through a less disorder. Also, it is endothermic. But in the case that the delta H is negative and delta S is negative, it's exothermic and the delta is going to a less disorder. So it's negative number, negative, negative is positive, negative number plus a positive number. We don't know, it depends on value of temperature. If the delta G will be negative or positive, right? So it's the temperature will decide this reaction to be spontaneous or non-spontaneous. Also, if the delta, so it depends on temperature. The third law of the thermodynamics is saying that the entropy of the perfect order pure crystalline substance is zero at absolute zero. So S is zero when the temperature is at zero, absolute zero. The entropy gonna be zero. Here we have done this before, finding the formation. So the standard enthalpy change of the reaction, delta H0, N multiplied by delta H of the product minus N multiplied by the delta H of the reactant. We have done it before. The delta S is entropy of the system. You can find it at the back of the textbook. Here is a table here, but you can go to the appendix and find that the entropy of each element. Standard entropy change for a chemical reaction. So N is the number of the moles again. So the delta G again is delta H0. All of that theta zero is a standard Gibbs free energy. Delta H is a standard enthalpy change, and delta S0 is a standard entropy changes that you can find these values at the back of the textbook. And T is at 298. This is standard ambient temperature. When you want to use those standards, make sure your T is 298 Kelvin. Click in this question. Calculate the standard Gibbs free energy change associated with a hydrogenation of ethane and interpret the result. So we go to the back of textbook to find the delta H formation of all of these elements here, compounds here. For C2H6 is negative 84.5 kilojoule per mole. For H2, I know is 0. Why? Because it's pure element. For C2H4, if you go back and check, it's 51.9. So the product should be minus the reactant. So the coefficient here is 1, 1, 1. So it's 1 multiplied by negative 84.5 minus. This one is 1 multiplied by 51.9 and 0 multiplied by 1. So we find that to be delta H0. The same thing you do for entropy. Entropy of the H element, you find it at the back of the textbook those. So the entropy of the product minus the reactant, you do the same way, and this is delta S. And since you are doing the standard, the standard ambient temperature is 298. Just delta H we have found it, delta S we have found it, and T we know. Delta G is negative. Delta G is negative again is saying it's spontaneous. Gibbs energy is decreasing. Here is another one. You do the same way. And here you find that Gibbs energy is positive. Therefore, it is non-spontaneous reaction. If the delta G is negative, the reaction is spontaneous. Delta G is positive, non-spontaneous. And if the delta G is 0, you're at equilibrium, no change, no direction happening. System at equilibrium. Now, temperature and equilibrium. So if the delta G is 0, we know the system is at equilibrium, right? So put the delta G 0 and the range for T. So T is delta H divided by delta S will give you the temperature that your system is at equilibrium. And T here, delta H 0 over delta H 0, T is absolute temperature, which the phase change occur. Means, let's say you're going from the solid to the gas or gas to the solid or changing a state. Look at this question. Use the Gibbs-Helmholtz equation and the concept of equilibrium to calculate the normal boiling point. Boiling point of the water is just phase change, right? It's from liquid to gas. So here, the delta H value of each compound is given. The S value of each compound is given to you. So we put it there. So, and we know the formula, when the phase change is happening, the delta G is 0 and you have T is equal to delta H 0 over delta H 0. Just need to find the delta H and delta H 0. I'm sure we can use for the delta H going to be product minus the reactant, product H2O2 of the gas minus the liquid, and the same things, product minus reactant for the entropy. We find that. And make sure you convert the entropy is joule per Kelvin. You need to convert it into kilojoule. So 1 kilojoule is 1000 joule. So that would be the entropy, and then delta H divided by delta S. Temperature is 370 Kelvin. We can convert into the absolute Celsius temperature. So the T in Celsius is T minus 273, 370 we got there. So the temperature in Celsius is 97 degrees. It's gonna happen. That would be the same thing. Just finding the temperature, and you can practice question number 3 and question number 4.